This is a lecture about complex numbers in trigonometry. So the one that A says, graph the complex numbers below on the same complex plane. Okay, so now how we do this is the x-axis. And this, in math, we use i's for complex numbers, and in engineering, they use j's for complex numbers. I'm going to use i's just because everything here is an I. But if you see j's for complex numbers, it means exactly the same thing. I'm going to say this is the same as yi. If I wanted to graph z1, okay, so I would go -2, which is right here, and then I'd go I went to, and that's really all there is to it. Let's say we have z is equal to a plus bi. This is called standard form. All complex numbers have to be in this form, where a and b are real numbers. The real part of z is a, and the imaginary part is b. When we graph it, we're saying that this is the real axis, and this is the imaginary axis. Okay, I think that makes it more clear. -2 goes in the x direction, -2, because that's the real part, and then -6. B, this is A. B is 5, and 1, 2, 3, 4, 5, and then up 4. So this is B. C is just 5. So that means it's on the x-axis. There's no imaginary parts. And D is 4i. So that would be 1, 2, 3, 4. So 4i would be right there. Trigonometric form of a complex number. We have a complex number z equals a plus bi, and we have the angle theta. This is exactly what we were doing with rectangular and polar. This is the trigonometric form. This would be the rectangular form in our book, because we would be able to evaluate this. This would turn into a rectangular form. That's the trigonometric form of z. And then r, which is basically the magnitude of the length of the line. We find exactly the way we always find the hypotenuse. See, and it's just the square root of a squared plus b squared, where a is the x value and b is the y value. And then we know that the tangent of theta, here's this theta we're talking about, is equal to the opposite over the adjacent. That's pretty much it. I really want to stress to you that it's very important to find the reference angle. I would rather you find this. And how you find that is you always make sure that you make this positive. Once you find the reference angle, put it in the correct quadrant. In this slide presentation, it's going to refer to the magnitude as the modulus, the angle as the argument. Converting a complex number from rectangular to trigonometric form. It's basically more like polar, where we have the magnitude and the angle. So state the quadrant of the complex number, then write each in trigonometric form. We have a negative and a negative, which is going to land us in quadrant 3. -2, -2. And so our point is right here in quadrant 3. State the quadrant, and then we're going to write this in trigonometric form. We want to find the magnitude. This is really the triangle that I have, right? Where this side is -2, and this side is also -2. If we want to find the hypotenuse, which is the magnitude, we can say that Z1, the magnitude, is equal to the square root of -2 squared plus -2 squared. And this is equal to the square root of 8, which is equal to 2 times the square root of 2. Now that's our magnitude. We know that the tangent of theta is equal to the opposite over the adjacent, which is equal to -2 over -2. I know that that equals 1, and that means that theta is equal to the inverse tan of 1. If it was negative, I would still make it positive and make it my reference angle, because it can't give me that angle in quadrant 3. If you look on a unit circle, remember that the tangent is the opposite over the adjacent. So when these two are the same, we always get 1. What angle always gives us the same numbers for the x and the y? 45 degrees. So we know that this reference angle is going to equal 45 degrees because this is the square root of 2 over 2 over the square root of 2 over 2, which is 1. But then we have to take it and put it in quadrant 3. What I'm going to do is add 180 to it, because that'll get me from 0 to this part of the x-axis, and then I just need that extra 45 degrees to make it the actual angle 45 plus 180 degrees, which is 225 degrees. Z1 is equal to our magnitude, which is our R, 2 times the square root of 2, times the cosine of 225 degrees, plus I sine of 225 degrees. And that's basically the form that we're looking for. So we're going to state the quadrant. I'll just graph it for you. You don't really need to graph it to state the quadrant. If you have 2 negatives, then you're in quadrant 3. If you have a positive x and a negative y, you're in quadrant 4. This one's going to be in quadrant 1 because they're both positive. I believe you all know this. If I were to graph Z2, it would be, I'll just call this 6, and I'll call this 2. So it would be this point right here. Now let's do the work. Z2 is equal to 6 plus 2i. The magnitude of Z2 is going to equal the square root, where this is 2 and this is 6. So it's going to be 2 squared plus 6 squared, which is equal to the square root of 4 plus 36, square root of 40, which is the same as the square root of 4 times the square root of 10, which is equal to 2 times the square root of 10. So that's going to be my magnitude. Then I can say, and I'm not going to keep going over how the inverse tangent works because I think I've done it in quite a few videos. So I'm just going to state that theta sub r, and our reference angle this time is going to be exactly the same as our angle since we're going to be in quadrant 1, but we're just going to get in the habit, and this is going to be the inverse tan of 2 over 6, which is equal to, obviously, the inverse tan of 1 over 3. And that is something that I would not know the angle for. I don't believe you would either. So I'm going to have to get my calculator out. I get 18.43 degrees. I would write this in the form of Z2 is equal to 2 times the square root of 10 cosine of 18.43 degrees plus I sine of 18.43 degrees.